Hello everyone, I'm gonna teach you something about probability theory, and the book is written by Richard Durrett from Cornell University, and the book is called Probability Theory and Example. And the third edition, which was written by Richard Durrett from Cornell University. Okay, and it will take like a lot of lectures to finish the whole book. I hope I will finish it in some day, maybe in a year, or I think in a year is enough to finish this book, and I hope you can follow my lectures. And the first lecture is, of course, from the first chapter, chapter 1, law of large numbers. Numbers. Okay, some basic definitions. First one is, sigma algebra. Not sigma algebra, probability space. Probability space is what? It is the triple omega, f, and p. Omega is called the outcomes, f is called the sigma field, or sometimes in mathematics we call them sigma algebra, and p is probability measure. It's a special measure. And sigma algebra is what? Sigma algebra is defined as follows. Sigma field, I will use sigma field in probability theory more than sigma algebra, but I always forget it myself to say it in sigma algebra, because mathematicians always use sigma algebra instead of sigma field. And the definition of sigma field is something, so it's actually a collection of subsets of outcomes of the whole space, omega. Collection of subsets of omega, so which means that the elements in sigma field is a set, but I don't know why they also did not mention the most important part of sigma algebra is that empty set is in the sigma algebra. Actually, you can find in other textbooks that sigma algebra always satisfies 3 conditions, but Durrett, the author, he just mentions 2 conditions for the sigma algebra, which I do not think is correct, which I think is wrong. It's not enough. So just to keep in mind that sigma algebra satisfies 3 conditions. So if you have the book, I recommend you to add one more condition to the definition in the book. The first is empty set is in the sigma field F, and then the second one is if A is in sigma field, we have complement of A also in the sigma field, and the third one is A1, A2, blah 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 in the sigma field, which we can conclude from this that a I equals to 1 to infinity, which also is in sigma field. This is the definition of sigma field. And then we define a measure. Measure is something a function is something we call the mu. Okay, this is a general measure, and we'll see something about probability measure, but we introduce the general measure first. Measure is something from F, okay, this is sigma field, to R, but R plus actually. And they also did say that he uses R, but I think it's R plus because measure is always a non-negative function. So R plus is fine, yeah. And then first property is mu empty set equals to 0, and the second property is mu A greater than mu empty set greater than 0. Okay, so this is equal to 0. So which means for any A in sigma field, which means for any A in sigma field, mu A greater or equal to 0. But the author just combined these two conditions together to just form a one condition. But I would prefer you consider this two as two conditions instead of one condition. And the third condition, which is the second condition in the book, is that it satisfies what we call them the countable additivity. So if AI pairwise disjoint, pairwise disjoint, which means that AI intersection with a J equals to empty set for any I doesn't equals to J, different from J, and then mu union AI I equals to 1 to infinity equals to summation I equals to 1 infinity and mu AI. This is what we call the countable additivity, and it's very important property as for measure countable additivity. So that's all. But probability measure has one more condition. Probability measure satisfies these three conditions, but one more, which is the whole space, the whole outcome is one. That's obvious, right? So this is a probability measure, and this probability measure satisfies four conditions: that P empty set equals to 0, P any event greater than 0, greater or equals to 0, and for disjoint event, the probability of the union equals to summation of the probability, which is the countable additivity, and the probability of the whole space equals to 1. But a general measure does not satisfy this condition. Okay. So let's study about the whole condition. Let's study about the exercise 1.1, which is first one is monotonicity. And monotonicity means P for any Okay, we should say a probability space first. Okay, say that we have a sigma, we have a field, and we have a probabilities, the whole space, what is the outcomes, the whole outcomes, omega and sigma algebra or sigma field, and then the probability on the measurable space, and this is called measurable space, and without p, but with p, this triple called a probability space or measure space. Yes. And monotonicity means for any A and B in a sigma field, A contained in B, then PA minus PB minus PA equals to PB minus A, while we have to, okay, and A minus B is defined as A slash B, okay, and A intersection with B complement, okay. But so here the B minus A, of course, is B A equals to B intersection with A complement, okay. And this is actually is very intuitional. A is contained in B, that's why the probability of B minus probability of A greater than 0, right? And P, okay, we'll prove it. Proof P B minus A equals to P B intersection with AC, which is by definition, and okay, since B intersection with AC intersection with A equals to empty set, then P B intersection with AC union A, these two are disjoint, and by the second property of, okay, by the third property of probability measure, which shows that if two sets are disjoint, and then the union, the measure of union equals to summation of union, the summation of measure, right? And then equals to P B intersection with AC plus P A, okay. And so since P intersection with AC, B intersection with AC union A by the operation of sets, which equals to B union A intersection with AC union A. B union A is what? B union A is B. Why? Because A is contained in B, and then intersection with A complement, union A is A whole space, which is B, okay? So this is PB, right? So PB equals to PB intersection with AC, which is B minus A by definition, and plus BPA, okay? And then we have PB minus PA equals to PB minus A, and since any set in the sigma field is with its probability greater or equals to 0, so greater equals to 0. Okay, the first one is done. The second one, okay, second one is subadditivity. Subadditivity. Say that AM is in F for M greater than 1 and A contained in AM, then PA is less than summation M equals to 1 PAM. Okay, and this is actually easy to prove since we have okay, proof. AM is in the sigma field for any M greater than 1, and A is contained in union of AM, then the probability of A is less than summation of AM. Okay. But since we don't have any information for AM, we don't know it's AM are pairwise disjoint or not, but we still have something very important technique in probability theory and measure theory, that when you want to make those sets pairwise disjoint, but with the same time the union of them are still the same, we can introduce another thing, BM, which is defined as AM minus AM minus 1, while M greater than 1. But we don't have a definition for A0, which means B1 equals to A1. Okay? And then for M greater than 2 is better. Okay, you can verify it yourself, I think. I'm not going to verify it for you. I think it's very easy, and probably you can verify yourself that BI intersection with BJ is empty set, and also by the same time the union of AM sorry, I think I made some mistake. I think here it's not M minus 1, it's something like I equals to 1 to M minus 1. Yes, and then this definition is perfect, I think. Yeah, it's this definition is good. Then you can check to yourself that BI intersection with BJ is empty set. Yes. And then PA equals to PA intersection with union M minus 1 AM equals to PA intersection with BM. Okay. Since BM are pairwise disjoint. Okay, no, not so fast. Yeah, so by the operation of sets, which means this one you can just change them, and we have this one A intersection with BM. Okay, and then by the countable additivity, I think, which is M equals to 1 infinity PA intersection with BM. Okay. And since A intersection with BM is contained in A intersection with AM, is contained in AM. That's why by the first one, the monotonicity of probability measure, that's P intersection with BM. So this one is by countable additivity. Okay, since A union BM, the set is pairwise disjoint. Okay. Why? Because BI intersection with BJ is empty set, so A intersection with BI intersection with A intersection with BJ is also empty set. Okay. And then this is how we can use countable additivity here. And then, okay, this is fine. And then, so it's less than PAM. Okay. And then we let this one equals to star. And then star is less than M equals to 1 to infinity PAM. Done. We are done. Okay, and then the third one is continuity from below, which is also important. Okay, continuity from below. Third one, from below. If AI to A then PAI to PA. So I will explain what is AI to A, which is up arrow to A, which means AI is a decreasing set. Oh no, it's an increasing set. It's an increasing set, which means A1 containing A2 containing A3, blah blah blah. And 2A means the union of ix to 1 to infinity of AI equals to A. So this is what we by the AI up arrow to A. It's very intuitional, right? So actually the proof is quite straightforward, and also we should rely on something. We use the techniques when we prove the second one, which is subadditivity. So actually you have to, okay, write something first. P k equals to 1i ai. This is fine, right? Because ai equals to union of ai. K equals to 1 to I, because everyone which is less than I, every index which is less than I, the AK is contained in AI, which means the union of AI, or AK, sorry. The union of AK equals to 1 to I is just AI. So this is by P I, K equals to I, BK, while BK is defined as something very, very similar as we exactly the same as we did for the last. So I equals to 1 to K minus 1. Okay. But we use I here, sorry. I will use another notation. So BK equals to AK minus union AJ, J equals to 1 to K minus 1. Okay. So you can check yourself that BI intersection with BJ is empty set for any I different from J, and the union of a BK is the union of AK, which is the same. So these are very important techniques. Why we use this? Because we want to construct a series of pairwise disjoint, which is BK, and at the same time satisfy the same condition that the union of AK is union of BK, but the AK is not pairwise disjoint. That's why we do it. And then we can do the summation of P BK, K equals to 1 to I, okay? And then we say that the limit of PAI is the limit of K equals, I equals to infinity, sorry. I equals to infinity, PAI equals to limit I equals to infinity, summation K equals to 1, I, P, B, K, right? And then this one is just summation K equals to 1 to infinity, B, P, B, K, and then we use back this countable additivity, which is P union of BK, K equals to 1 to infinity, and then since P union of BK is union of AK, which is by the definition of BK, and then this is B equals to P A. Oh, we're done, right? And then we prove the continuity from above, which is exactly similar to the proof of continuity from below, but I will say something more about continuity from above, which is slightly different. Okay, so since I forget to write down the problem. If AI down arrow to A, then PAI down arrow to PA. Well, this is, down arrow means it's a decreasing set. Decreasing sets are not decreasing number is set. So it's kind of similar, but you have another definition. So AI down arrow to A means, means A1 contain A2 contain A3 contain blah blah blah, and at the same time the intersection of AI I equals to 1 to infinity equals to A. Okay, this is the definition of down arrow to some set, a sequence of set which is decreasing. Okay, so the proof is similar. A1 minus AN up arrow to A1 minus A. Is it obvious? If you don't think it's obvious, you think it yourself. You check it. I think it's obvious. And since AN is containing A, which means A1 minus AN is an increasing set, because AN is decreasing set, right? And then it increases to A1 minus A, and then by what we have before that, you consider A1 minus AN to this, and then we have probability of A1 minus AN to PA1 minus A, okay, by 3. Okay, and PA1 minus PAN, PA1 minus PA. Is it okay? Since this one is by the first one of the exercise. Yeah, by the monotonicity. You can see that if A is containing B, so PB minus PA equals to PB minus A, which means because AN is containing A1 for any n greater or equals to 1, which means this one holds, right? And okay, we can also write something like this. Yeah, it doesn't matter. And which means limit PA1 minus PAN equals to PA1 minus PA, which means limit, because we cancel PA each side, this is constant, right? PAN equals to PA, and we are done. Okay, but I have to say that you should be aware of something, which shows that the probability measure is always the case, that you can always use continuity from above, but for other general measure which may not hold for continuity from above. Why? Because you can see that PA1 minus AN is not always equal to PA1 minus PAN if PAN is infinity, or PA1 is also infinity, because by the monotonicity of measure, which means that PA1 is always greater than PAN. So if PAN is infinity, PA1 is also infinity. So we have like infinity minus infinity, which does not make any sense. Okay, so you have to be aware that for like for Lebesgue measures, and this does not always hold for continuity from above. So for Lebesgue measure, we have one more condition, which is that PA1 is less than infinity, or PAN is less than infinity for some n, but you must have some n that which let the PAN less than infinity, and then we can use the continuity from above. Okay, but we don't have to worry about improbability. Why? Because P of the whole space equals to 1, which is less than infinity, obvious. And then any subset of the whole space omega is also with probability less or equals to 1, and also it's at the same time it's less than infinity, and it's so we don't have to worry about those stuff for probability measure. Okay. And we're going to talk about the example 1.1. Which means omega countable outcomes. F is the collection of all the subsets of omega, which we have a special notification for those sigma field, which we will denote as power sets of omega, and power set we call them, which represent that it's denotes all the collection of all the subsets of omega. So it's obvious that it's the biggest sigma algebra, right? Because it contains all the subsets of the omega, the outcomes. So, but you have to be aware that because omega now is countable outcomes, so the power set of omega is fine. Then we can have a probability measure on that, but you have to be aware that if omega is uncountable, which so you won't have a probability measure on the power sets of omega. So you have to worry about it, and this has been solved by a lot of mathematicians before that. They constructed some Borel set and then have the measure on the Borel set. It doesn't have any paradox, but you have to worry about that power set of omega is a dangerous thing whenever the omega is uncountable. It's very dangerous. And then we have P A equals to summation omega belongs to A P omega, where P omega greater than equals to 0 and summation omega in omega P omega equals to 1. This is one definition of a probability measure, and actually it's very easy if you have a P omega equals to 1 over the whole number of the number of points in the outcomes. For example, if omega equals to heads and tails, then the cardinality, sometimes these are called cardinality of omega equals to 2, and then P the heads equals to P heads equals to 1 over 2, right? It's obvious. And P heads tails equals to P omega in space, which is 1/2 plus 1/2 equals to 1, obvious, because it's the whole space. And then we have another example if omega equals to 1, 2, 3, 6, and the cardinality of the omega is 6. And then P 1, 2, 4 equals to, oh sorry, this is probability. This is little p, yes, little p omega, okay, and equals to omega in, yeah, I equals to 1, 2, 4 pi equals to 1/2, right? This is a very easy example. We will look at the second example, example 1.2. And see, R is a real line, and B is a Borel set. Borel set is the smallest sigma algebra or sigma field containing open sets. We have a lot of things to talk about with Borel sets, but I'm not going to talk about it now. It seems that it contains all the open sets, the Borel set, but at the same time, the Borel set contains all the closed sets, half open, half closed, all kinds of sets which you can imagine in your mind. Okay? Lambda is a big measure. So lambda A B equals to B minus A, and lambda equals whole space equals to infinity. And this is proved to be a probability, proved to be a measure on the real line with Borel sets. So this triple is called a measure space, right? And it's been proved. It is a measure space. And then how do we change lambda to some probability measure? Can we restrict a Lebesgue measure to a probability measure, because Lebesgue measure don't satisfy the condition that the lambda of the whole space is 1, but the lambda of subspace is infinity, so we can easily do it by let the whole space just equals to 0 to 1, and then the Borel set is restricted to some set like this for any A in the Borel set. This is, and PB equals to lambda B for any B in the Borel set. For any B in F. Okay, so is this triple a sigma, a probability space? Is this triple a probability space? You have to prove it because you don't know it right now. But probability space is triple, right? It's also triple. It's like omega. This is sigma field. This is probability measure. Okay, so you have to verify it. So P omega equals to 1. Okay, verified. And these three conditions. Okay, I think we should start with verify that F is actually a sigma field. Otherwise, it doesn't make sense. Okay, so F is a sigma field. Okay, we check it. So as empty set is in the Borel set, and the Borel set, okay, because Borel set is a sigma algebra, it has already been proven. I'm not going to prove it right now. We have this. Okay, so empty set is in Borel set, which means empty set intersection with E is also a empty set. So by definition, empty set is in F. Okay, and then A in F. I show that AC is in F. Okay, how to show it? A in F, because A is in F, there must exist A star in B such that A star intersection with A1, intersection with 0, 1 equals to A. Yeah, this is just by the definition of how the F is formed. Okay, and A star is in B, and B is also B is a sigma field, which means A star, the complement, is also in B. And then A star, the complement, intersection with 0, 1 equals to A, the complement, which means A, the complement, is in F. Okay, you have to notice that A star, the complement, is with respect to the whole space, with respect to R, while AC here, the complement is with respect to omega, which is open set 0 to 1. Okay, and this is kind of different complement. When you say complement, it's something that you have to worry about what is the whole space, what is the complement. Otherwise, it doesn't make sense when you say complement. Okay, so A's complement is also in B, though the complement is like with respect to R, and A star C intersection with 0, 1 is the complement of A, which is with respect to omega. Okay, and then since this one is in B and by the definition, and by the definition of the F, which means the AC is in F. Okay, and then and last thing. And last thing is the countable union. Okay, and so A1, A2, blah 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 is in F. Show that. Okay, show that union of AI I equals to 1 to infinity is also in F. Okay, so since A1, A2 are in F, so exist A1 star, A2 star in B such that AI star intersection with 0, 1 equals to AI. Okay, why? Because AI is in F, and how is F is formed? F is formed by choosing any set in B, so they must exist A1 star which satisfy A1 star intersection with 0, 1 open set equals to A1, so for any I. Okay, this is trivial. And then it's obvious that AI star union of AI star is in B, so the union of AI star ix to infinity intersection with 0, 1 is also in B, which means the union of AI let me see. Okay, the union of AI intersection with 0, 1. This is by, these two are the same. This is by the law of operation of set, okay, of sets. And then also in B, which means union of AI is also in, oh, this is in F. Okay, since this is in B, so this is in F. By definition, okay, this is in F. And then this is in F. Okay, we are done. And then we look at exercise 1.2, and which is show that Fi is a sigma field for any I, sigma field. Exercise. (1.2). Okay, Fi I in I, sigma field, and then intersection of I in the, this I is called the index set. The index set is something like 1, 2, 3, 4 natural number, but you have to remember, you have to keep in mind that index set is also could be uncountable. Index set anything. It could be R, okay? So this intersection of set, okay, this is set. The intersection of set is also it also could be uncountable intersection, okay? This is something you have to keep in mind. Could be uncountable. And is also a sigma field. Okay, but I think this is quite easy to prove, I think. You can prove it yourself. This is left as an exercise. You keep in mind what is the intersection. Intersection with me, which means every element is in the set. Okay? And then the second thing is that you should keep in mind that Fi is a sigma field, and you use the properties of sigma field, and you keep in mind the definition of sigma field. You can prove the three conditions of this intersection is satisfied, and this one is also a sigma field. Our left is that exercise. And also that's one notation of this one is the smallest sigma algebra. Sigma field containing A. Okay, A is a collection of subsets of the outcomes. Okay, you keep in mind that this A may not be a sigma field, because you could just write omega, which if omega equals to 1, and then you could write that 1, okay, a could equals 2. Sorry, a could equals 2, you know. 1 empty set, 1, 2, okay, and then the smallest sigma field continue. Okay, that we have to say that A is not sigma algebra, okay, or sigma field, because you can check that the 3 conditions that verify that A is not sigma algebra, but it could be generated to a smallest sigma algebra, which is, I think, is A1. If the whole space is if the whole space is 1, 2, 3, okay. If the whole space is 1, 2, 3, and should be 1, 2, 3, sorry, 2, 3, 2, 3, and 3, and 2. Well, yeah. Okay, this is the power set. Okay, let me check and change something. It's 1 empty set, and then 2, 3. Yeah, and then I will get you some smallest sigma algebra, which is it's the sigma algebra generated by A, which is not a power set of the omega. Okay, let me see. So is this one. So it is a sigma algebra, right? So it must contains and the whole set 1, 2, 3, okay, and then 2, 3. Yeah, that's all. It's obviously smaller than the power set of A. Okay, so that's called the smallest sigma algebra containing A, and you can check that this one is actually indeed a sigma algebra. Okay, and example 1.3 says something about the product of probability space, and it's something trivial, but actually there are some interesting problem in product space. We will see in the appendix. If time is possible, we will talk about something in the appendix and introduce some theorems in the product space, but product space no. Now I want to skip this, and okay, this is the first lecture of the course. I would say this course may be called probability theory. Yeah. Okay, and the textbook again is written by Richard Durrett from Cornell University, and the textbook is called Probability Theory and Examples, and it's 3rd edition. And that's all. Thank you.